Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world.
So for today's podcast, we've got a really interesting episode. I know I always say that, but actually genuinely, I think today's will be fascinating. It's in a subject area that's really close to my heart and something that I'm going to really enjoy talking about. I'm joined today by Nabeel Shirazee, who is the global CTO of a really interesting business called ePropelled. So welcome to the show, Nabeel. It's great to have you here.
Yeah, good morning. Thank you for having me on the show.
And if we could just get started by learning a little bit more about you, and if you could tell us about your background and how you came to be doing what you're doing now.
So, as a child, I've always loved science, and I've been playing with different instruments to get me into sort of that mode. So I started my first degree in electrical and electronic engineering because these electronic chips always interested me, and I used to open old radios and other electronic gadgets to see what's inside them. So that fascinated me and put me on the track to do this course. When I completed my electrical and electronic engineering, I was fascinated by magnets, permanent magnets.
Okay.
I thought, why not do a master's in magnetic engineering? So I applied to various universities and got a place at Cardiff University where they were running a course in electromagnetic engineering. So I started this course. It was 1 year's magnetics course, and I won the prize for the best project in the department. So I thought, I'm doing really well in this. And the magnetism is so important because it's all around us. Even the Earth has got magnetic field. So that grew my interest further into magnetics, and I thought perhaps I should do a PhD in magnetic engineering. So that led me to do 4 years PhD in magnetic engineering, where we were looking at electrical steel of electric machines.
So this master's course, it sounds quite quite often you sort of focused on electrical machine design, but it sounds like it was a bit of a broader church than that. What kind of things were you looking at?
Yeah, so during the master's course, we were looking at the material science of actually electrical steel. We were also working on high voltage programs as well, which was being run at Cardiff University. So it was high voltage, it was material science, what is making, the materials and how to improve the efficiency of materials. So that was happening during the master's course. And we were also looking at, materials which actually produce high flux density. So all that sort of, got my interest deep into material science and led to a PhD.
Cool. And I guess, so you mentioned high voltage there, but I'm guessing that's proper high voltage, not what us EV people talk about as high voltage.
Yeah, that's proper high voltage, which you see in lightning. So, the Cardiff University is famous for doing that kind of work. Even today, they have that department, and we are actually working with them to see what the effects of lightning strikes are, etc.
They've got a very good high voltage lab there. Cool. And so you did your PhD.
So during my PhD was sponsored by European Electrical Steel in Newport. So they had an orbs work where they've been working on electrical steel, and they supported my PhD. And during that time, I was playing with a lot of magnetic instruments and came up with the idea of magnetic levitation during that period as well. How to create magnetic levitation. And that became really an attraction for the university. And in fact, I even entered the competition in US. In Pittsburgh, it's a trade show. It's a invention show, and I won the first prize in USA, which then led to several articles being published in magazines, and then the interest grew of other people trying to contact and to see what is material science about, how we are looking at materials, how we are improving materials. Not only in electric machines, but other
applications. Yeah.
Yeah.
Yeah, it is. I think people. Well, it's easy to forget, isn't it? You mentioned some magnetic fields being all around us. See, Earth has a magnetic field, but we're using the principles of electromagnetics in electric motors, and we talk about motors a lot, and we will talk about motors some more today, but also in all kinds of other applications. So like the electrical grid depends on transformers, and that's a really key electromagnetic system. So it's such a huge part of our everyday lives, the relying on electromagnetic systems and technology. So big area.
Yeah, it's a huge area, and for that reason, I thought perhaps I can make a career out of it. And while doing my PhD, I started a company, Electronica Products, where we could look at electric machine design and also power electronics at the same time.
When did you start Electronica Products then?
Well, Electronica Products actually started in December 1998, so that's a long time ago. But I was still working, at the university, and decided to do some consultancy work. And that came about because a lot of articles were published on the magnetic levitation system. So an aerospace company approached me and said, oh, they've got an issue with one of the motors, and can we improve the air gap inside this electric machine? Because they've seen the magnetic levitation system had a large air gap. And that led to, consultancy programs with aerospace company, and then Electronica got a foothold in designing electric machines, and that led to several other programs, which was great. And working for the aerospace companies, initially they didn't believe that I could come up with the answers, because it was like, I was myself. Whereas they said they've got 45 engineers working on this right now. That was a great challenge. So they gave me an opportunity. I had formed a team by then of 3 or 4 people, and we said, give us the challenge. They gave us the challenge, and we actually came up with the answers. Initially, they thought the design wouldn't work when we presented, on the computer simulations. But they further gave us the opportunity to make the prototype, and their chief engineer was here in Cardiff when we were doing the testing, and he was amazed that actually it did work. So it was brilliant, and because of that, they came on the bidding list of the A380 Airbus at the time. So that was a great project and a great success for us at the time.
Fantastic. And then sort of turning the clock forwards a bit, how did you start to work with ePropelled?
At the time, then we started working on different electric motor machine programs, and in 2003, came up with an invention called magnetic gearing at the time, where we were working on a technology which would improve the performance of electric machines. So that plus other programs of electric propulsion system, then you fast forward to 2018, where I met Nick Gruel, and he was, really keen in working in the field of electric motors, efficient electric motors. So we had a great chat and decided that perhaps we should merge together. And he formed ePropelled, and we joined forces, and we said, okay, let's work together and improve the electric propulsion system, which the world needs, because electric machines are moving very fast. The whole world is going electric. Everyone wants an electric motor. So we thought this is the right time for us to propel in this field.
Cool. And because you're still based in the UK, and Nick is in the US, is that right?
That's right. I mean, Nick is originally from the UK, but yeah, he's spent the last 40 years in US. So you can say he's based in USA, yeah, and me in UK. But we have got great synergy. We work together well, and it's great to form this partnership where we think we can change the world.
And that kind of leads us neatly into talking about ePropelled. So what is it that you're doing at ePropelled now? Tell us about your technology and a bit more about the business.
So ePropelled is all about electric propulsion systems. And ePropelled is designing intelligent motors, motor controllers, generators, power management systems. And the goal is to help technology reduce the power consumption, energy consumption, and reduce carbon emissions, and increase the efficiency of the system at the same time. So we believe that we are leaders in magnetic engineering, and we really want to make aware to the world that it's not about just design, but it's about material science, how you produce materials, how you improve the reduction of carbon emissions right from mining the raw materials. ePropelled is also about filing patents. We've got over 40 patents. We've got now over 40 engineers, professionally qualified engineers as well. And we believe that we are the future of electric propulsion.
Are the patents is it one sort of particularly strong kind of technological advancement that you guys have made in e-machine design?
So one of the technological advances we've got is called EDTS, which is efficient dynamic torque switching. And what this does is it reconfigures the windings inside an electric machine. So it works like a gearbox, where it changes the torque of the machine as it speeds up. So the advantage is that you can operate the electric machine at different efficiency zones, right? So if you reconfigure the windings, it gives you an increased efficiency band in the speed torque range, which means that throughout the drive cycle of an electric motor or electric vehicle, the efficiency is greatly increased, which means that you increase the driving range by at least 15%.
And when you say reconfigure the windings, I mean, trying to, in my head, envisage an electric motor as quite a fixed thing with, how do you reconfigure the windings on a machine dynamically?
Right. So what we do is the wires are wound in parallel and they come out into a switch matrix. So this all happens within the casing of the electric machine itself. Windings go into a switch matrix, and that switch matrix, whether it be a mechanical switch matrix or a semiconductor switch matrix, you can reconfigure the windings by changing between series, parallel, or its combination of windings. So literally, you are changing the number of turns inside the electric machine while the machine is running.
So you kind of, where you might normally have like a shorting ring connecting all the windings together in a normal machine, you've replaced that with a electronic circuit, basically, where you can sort of switch around how the windings are connected together.
Exactly. That's what we do. And the performance increase is phenomenal. And not only that, it reduces the size of the electric machine as well. So we are talking to several OEMs right now who are very interested in this technology, and we are doing simulations to show the full benefits. So it's not just increasing the driving range, it's increasing the efficiency, overall efficiency of the powertrain, and it's also reducing the battery size.
It's always a sort of big trade-off with the motor design, where, and particularly in passenger car, where the motors tend to be quite oversized for sort of power. So you end up with a lot of torque and fast acceleration, which is great. But under sort of normal driving, if you're not using that power and torque, actually the light load efficiency of the system can be quite poor. And I guess you're able to adapt to that. So you could change the machine characteristics to suit the driving conditions.
Absolutely. So we're changing the machine characteristics while the machine is running, and that's a big advantage to the system. Means that you need less active material to manufacture the machine itself as well. So we've got shift maps in the software, which looks at your speed, your torque requirements, your current, your voltage. All the parameters are looked at. And because it's looking at these parameters and looking at the efficiency number, the software will decide which winding configuration is most efficient for that driving speed and torque. Yeah, so we've done the simulations, and it's amazing to see, when it says that you need to shift from say parallel winding to series winding or its combinations. And normally what happens is it tends to go into a parallel winding because that gives you the most efficient combination, because the resistance is very low. So your I²R losses are very low, especially for high speeds. And it allows us to operate in a speed zone where we don't need field weakening. Normally, a standard electric machine will require deep field weakening if you want to go much faster in speed. And we don't need that because we reconfigure the windings in parallel at high speeds.
Right. Okay. That's really interesting. So field weakening is a big issue or phenomena, not just because you're effectively injecting current to knock back the rotor magnetic field, so it's costing you energy, but it also tends to make the rotor get hot.
Absolutely. So that we don't need. So we don't need deep field weakening because we reconfigure the windings. So if you reconfigure the windings, means that technically you reduce the number of turns, which means that the back EMF required, it drops. So at higher speeds, you can, get your optimal performance. But normally what happens in a standard machine is as you're speeding up, your back EMF is coming close to your bus voltage. And to then back off, you have to apply this D-axis current to weaken the magnetic field. Yeah.
And does that mean, because one of the reasons people like or have sort of shifted to using the interior permanent magnet type motors is that they can you've got the sort of permanent magnet field, but you've also got a reluctance torque as well, and you can sort of bring that in and out. Would that mean if you applied your technology, you could sort of extend the sort of usefulness, if you like, of a surface permanent magnet machine to sort of get into that region? Or would you also apply your technology to an IPM machine as well? Is there a difference? Or?
Right. So we are applying the technology to both surface permanent magnet and the IPM machine. So it's very interesting to see how we can benefit the IPM machine as well, which most of the manufacturers are currently using. So the D-axis current, if you apply a little amount of D-axis current, it does give you the reluctance torque. But to go deep into a high speed, you need that extra field weakening to be able to go into the high speed region. So we don't need that. So we can benefit from the reluctance torque and switch the windings and be able to go at high speed and maintain very high, extremely high efficiencies of over 98% during the drive cycle of the vehicle.
So really interesting, really interesting. There's, I can think it's at times in the past been involved in sort of machine developments, particularly high kind of pole count machines as well, which you tend to have to back off from that.
That's right. So it could allow us to have a high pole count machine as well. Not that we may require that, but that's also possible, and we are very fortunate to have won several grant awards, so we, which allowed us to do a lot of experimental programs. So we won SMART Award from the Welsh government. We won the Innovate UK Award, Carbon Trust Award, and also we won some Aerospace Technology Institute awards as well, to be able to help us do the research and development and get to the stage we wanted to get to, so that we can, commercialize these projects into products.
I've got some more questions on the sort of technical aspects of it. I'm interested in how you do this, the switching of the different windings, and if you end up then effectively with, because in a normal motor controller, you've got your bridge circuit. We normally have 3 sets of switches, high side and low side, and that's sort of a standard 4-quadrant inverter. If you're then controlling multiple systems, do you kind of have the same inverter but then with a secondary set of switches after it, or do you effectively have just more stages to the bridge that you can run in sort of series or parallel with each other?
Right. So we've got two systems. One is where we are using a standard inverter, even though the inverter is done by us, right? So it's just like a standard inverter. It's got the standard IGBT modules, and it's connected to a separate switch matrix. And switch matrix is just an array of switches. And we plan to compress that size to a very small, compact, custom designed switch matrix so that it becomes very small. So that can be mounted on an inverter as well, if you like. It can be part of the inverter or part of the electric machine, unless the inverter also becomes part of the electric machine, because you want to keep the windings as short as possible. So if you keep the switch matrix separate, then the windings which come out of the machine, of the electric motor, go straight into the switch matrix. And the link between the switch matrix and the inverter is just the 3 phases, right? So you just control the 3 phases normally through the inverter. And when you actually switch, you already know, because we've mapped out the complete machine before. It's like a second or a third or a fourth motor. So it's like if you've got 4 combinations of winding, it's like 4 motor in one.
Yeah. So you have to just change the characterization map that you're running at any one point in time in that.
So the inverter already knows. So when the inverter is changing, say, from configuration A to B, it already knows that it's going to go to B, and it uses the B parameters as soon as it switches. And the switching can be as fast as in microseconds, right? So the switching is very fast, and it changes, it's like operating a motor B rather than motor A, and then goes to motor C, and goes to motor E. And the parameters are already pre-fed into the machine and into the software. So it recognizes before it ships that it's going to be those parameters, because it's important to know what machine you're running for the inverter all the time.
Yeah, I guess, and if you're doing it like that, you probably can manage the point at which you're switching so that you're not switching under full load and things like that as well.
Correct. I mean, although we can, switch without any load, we are looking at on-load switching as well, which is very interesting. So we are working in that field right now, working with semiconductor companies to ensure that, that is safe and good to do so with high current flowing in it. So it is very exciting times, it's very exciting times for us. we want to be the leaders in this, not only in how you do the switching, but how you control it, how you maintain it, how you, service it later on, how to ensure that the complete propulsion system is fully aware of, the aging process even, and increase the lifespan of not only the motor and the inverter, but also the battery, how to manage the current in the battery to reduce the current draw to keep it, as low as possible. So you extend the life of the battery and the driving range.
Mm. And I guess you mentioned just now in sort of passing, you've had some grants and you've done some work, and you mentioned the ATI, which the Aerospace Technology Institute. So obviously a pretty good indicator that you see the applications for this beyond just the automotive world and in other fields as well.
Correct. That's absolutely right. And we are very excited that, we are thinking beyond just the EV, but into the aerospace sector and how we can electrify the aerospace sector, because as you know, there's a big drive towards zero carbon emissions by 2050. And, the aeroplanes also have to help towards that. And we see that the technologies can be applied to the aerospace, how to design bigger machines. By bigger, I mean bigger power capacity, say up to a megawatt and a half, but keeping the size down. So traditionally, the kilowatts per kilogram, the specific power density is hovering around, I would say, 10 kilowatts per kilogram to say, some claim they've got as high as 15 kilowatts per kilogram. But our target is to increase that to at least 25 kilowatts per kilogram. And that's a huge jump. And to be able to look at such increase in power density, we have to look at the material science. We must understand the material, not only by using more material, but how to improve the performance of the material, to work with suppliers and, increase the capability of the active material so that the machine gets smaller, we use less material and still yet give high power density. And
is there a particular thing that, would you say this is your dynamic torque switching technology is particularly suited to high speed machines or low speed machines, or is there a particular area that you feel that it really brings the biggest advantage?
Right. So the biggest advantage comes when you are actually moving from a low speed machine to a high speed. So if you've got a varied speed range, that's where it benefits, because you can have fixed winding, which is good for a small speed range where it will give you optimum efficiency. But if you need low speed and if you need medium and high speed, that is where EDT is beneficial, because it switches between the windings. It gives you good performance, extremely good performance at medium speed, extremely good at low speed, and super performance at high speed. So it literally broadens the constant power range of an electric machine and the high efficiency zones throughout the drive cycle or throughout the efficiency map of the machine.
Okay, I see. So then, because the big trend in automotive over the last couple of years has been moving from lower speed motors, so typically up to 8,000-ish RPM on the sort of first generation EVs, to higher speed motors, typically around 20,000 RPM on newer machines. And that the OEMs have been doing that, so vehicle manufacturers are doing that to basically use smaller motors so they can spin it faster, they get the same power, but then they have a very big reduction ratio in the gearbox. However, the machine designed for that to have enough torque at low, it's that must be playing right into your kind of space, that move to this much broader speed range.
Absolutely, it is playing in our hands. And the manufacturers are looking for gearboxes which can give them an advantage. But we think that this EDTS technology is giving us such superior performance, and you don't need the gearbox itself anymore. Right? So you get rid of the gearbox. The machine speeds, as you pointed out, they were 8,000, around 8,000. They went to like 15, 16, and now they're into 20,000. And actually, they're like 28 to 30,000, approaching that kind of speeds. And if you have that kind of speeds, then you do need a gearbox to, of course, increase your torque.
Like a single speed reduction gearbox, typically, though.
Yeah, like single speed. But if you go too high in speed and have a high reduction, then you are playing with efficiency there as well. So you are compromising certain amount of efficiency.
It's a good way to give a gearbox designer at least a headache, if not a series of nightmares. 30,000 RPM gearbox, please, sir, that's going to go in an automotive application. That's difficult, to say the least.
Yeah, but I think there are a couple of OEMs who are 21,000 RPM and about 27,000 RPM already they're working on. So if you're at that kind of speeds, then a reduction gearbox efficiency becomes very important as well. But if you bring EDTS in it, then that helps reduce the reduction box size, the ratio. And increase the efficiency that way. So we are doing some really great simulations to see where is the balance between the reduction, the EDTS, and the size of the machine and the speed of the machine to increase the overall efficiency of the drive cycle. That's the ultimate aim, because increasing the overall size of the powertrain means that you're reducing the carbon emissions that much more.
Yeah, interesting. And the whole sort of issue in terms of vehicle efficiency and range, it's now a really important topic. In the past, people didn't buy cars really. I remember some research into this. The efficiency of your car when it was a combustion engine was important somewhat, but it wasn't one of the main purchasing decisions. But with an EV, the range is now one of the really, really important, and driving cycle range, but also real world range, like what people can achieve in practice. It's one of the major buying decision indicators for EV purchasing. So a lot of people focusing on efficiency and trying to extend it.
Yeah, I would agree that a lot of people are focusing on efficiency, and longer driving range, which is important to people, but without increasing, the size of the battery pack. I mean, that's the challenge, and I believe with EDTS we are up for that challenge, where we believe we can increase the driving range. At this moment, we are saying it's at least 15%, but I believe with new technologies, new materials coming up, we could push it as much as 20 to 30% improvement in driving range, and it's all about how to achieve this with the least amount of, essential materials used. Because if the world is going toward electrification, everyone will need electric motors, and everyone will need the bits which make up the motors, which is the magnets. If you've got a permanent magnet machine, you need the electrical steel. Even if you have magnet-less machines, they need electrical steel. They need the windings, whether it be aluminum or copper. And these are the bases which make up the motor, how to use these materials effectively so that there's enough to go around for the whole world. you know.
And so I asked you before about permanent magnet technologies, and you've talked about interior and surface permanent magnet machines and how your tech works with that. But the other sort of two, the one more common type of machine out there is an induction motor, and then you've also got people doing developments on switch reluctance machines, which are magnet free, like just mentioned. Does your technology kind of have an interaction there as well?
We do. Well, in a way, we've looked at the induction motor and we've looked at efficiencies inside an electric, induction motor. And people are playing with that technology. Not only that, but also wound rotors, where you've got copper winding on rotors itself. So it all comes down to efficiency and the material usage. So if with our EDTS technology, what we are doing is we are using permanent magnets, but reducing the amount of permanent magnet we are using. So the quantity of magnet is going down. In a switch reluctance machine, you don't have magnets, but the size will be always bigger, and it'll always fight with that efficiency. So it comes down to, not just the magnet, but electrical steel and the wire or winding we are using, be it copper or aluminium. So it's how much of this active material we are using. They all use active material. One uses permanent magnet, the other doesn't, but reduction of magnets and improvement of efficiency is key. And I think inherently switch reluctance machines, are getting there, but they've got other issues like torque ripple, noise, etc. So people are improving all that, but it also comes down to how much electrical steel you're using as well, not just magnets. And in induction machine, of course, you've got copper bars or aluminium bars inside it, so that's also using quite a lot. And the efficiency is not as good as a permanent magnet machine.
And I was just wondering if because obviously the thing about those two, three technologies actually, because wound rotor is similar in that you've got another variable in that you can play around with the rotor magnetic field strength now in terms of on that cycle. So if I could change the winding configuration, and also, does that just make it too complicated? Or is
it all comes down to the control strategy, and it is also the manufacturing cost. So how to make it a viable product? I mean, there's no point designing something which you can't manufacture and sell. We believe that wound rotor will help with that, but at the end of the day, that also comes at the cost of efficiency. If you've got a wound rotor, you've got losses there as well, because you've got windings and it's got I²R losses. You have to live with that. There's a balance between what materials you can use and what's the most efficient way you can actually put them together with least amount of disruption, and also how you mine them and all that stuff, how to care about the environment. At the end of the day, the main driving factor is reduction of carbon emissions. So if your mining process is not supporting that, then we have to look at that and see how we can help support the overall equation of carbon reduction, increasing efficiency, and reducing cost of the powertrain, be it in aerospace or automotive or in the marine applications.
Yeah. Well, so my next question was going to be, is there a particular application that you are most excited about, where you see early adoption potentially for your sorts of technology? Where do you see you going first?
So the early adoption will be in the EV market, and I'm really excited about that. We are very close to bringing the product to market, and we are working with major OEMs to work with them to show the benefits of this technology. So I would say the automotive market is the first market, but I'm very excited about the aerospace market as well, because I think we can make a big difference in the aerospace market, and bring the technology in that field as well. And it's not just with one patent. It's with several different patents which we are working on. We believe will help in reduce carbon emissions and reduce the materials which we are using for all applications.
One of the main things today, you've been involved in the field a long time, since at least 98, and before with your PhDs and studies and things. But there aren't that many people with the sort of experience that you guys have got about in the world at the moment. And so just even without patents, the sort of know-how of how to develop more efficient powertrain systems is very important.
I think it's very important, as I was very fortunate to start working with electric machines, at the turn of the century. And
I don't say that. That sounds like it.
But yeah, I started looking at electric machines, I would say, seriously from 1999.
God, the turn of the... That sounds... you've given me a headache now. At the turn of the century. Oh, my God. Yes, it's technically correct, but it just sounds such a long time ago.
Yeah, but I was fortunate enough to work in this field right from the beginning, where I had external company, an aerospace company, approach me and say they've got a challenge, they've got an issue, they've got a problem. Can I solve it? And the answer was yes. And it took some convincing to convince them that give us the program, and they did, and we delivered. So that led us to really believe in ourselves, because you must believe in yourself that you can actually achieve these things. And the experience we've gained over the last 20 years has been amazing, working with different OEMs, working on different electric machine programs. And one of the, I was lucky enough to work with European Electrical Steel, who make these electrical steels. What are the challenges in making these electrical steels? How to improve the performance of these electrical steels? So all that has been, part of the experience. Not only that, working with permanent magnet suppliers and manufacturers, how to improve the strength of the permanent magnet. So, we've had some exciting times working alongside these companies, help improve the materials, and giving us that experience which we've got today. And for that reason, we believe that we are leaders in magnetic engineering, not only just for a few people, but we are teaching all the upcoming engineers about this, and for them to learn and appreciate, what this is all about for the foreseeable future.
You mentioned, so maybe I'm going off on a little bit of a tangent here, but you sort of made an interesting point about, you've worked closely in the past with magnetic steel suppliers and permanent magnet suppliers. Do you see a problem in that, in sort of the UK and Europe, and the US actually as well? We've not really invested properly in the sort of underpinning technology like the steel, like the permanent magnets, and we've kind of just dirty commodity, and we've sort of let Asia kind of take the lead on that. Do you see that as a problem for us moving forwards, or do you think that it's coming back?
I think that it's unfortunate that we closed, mothballed some of the facilities. But I believe this is the right time to get in it. I think I'll be so happy if people invest in the steel industry, especially in the UK and even in US and Europe, because this is coming big time, in the sense that if everyone needs electric machines, we need to invest in the elements or materials which actually produce them. And although I've seen a decline, I think this is the right time to get in it. I believe that there are materials in the Far East but they are not as good as what we can do in Europe and US. And in fact, Japan as well is part of the material supplier. And most of the material which is coming is produced in Europe. India is coming up as well, but I believe that UK especially should play a bigger role in this active material area. I believe, it's the key. It's absolutely the key, and we should get in it now.
Yeah, we having been at the forefront of sort of steel manufacture historically, right back to the Industrial Revolution. And I saw someone post a picture the other day, and it was of I can't remember where it was. It was somewhere in the UK, which was the first sort of industrial steel mill to use coal in the process of making steel instead of charcoal. And obviously there's a sort of negative story there in terms of this is the beginning of climate change and all the rest of it. But the positive story of that is actually that, the steel industry did start in the UK, basically, in this sort of proper industrial production beyond using charcoal. So you need carbon in steel, but it's moving forwards, interesting things happening with low carbon steel production and stuff like that.
And I just wanted to make another point, is that it's about production, but it's also about recyclability, about sustainability. It's important that we are able to recycle all the machines coming offline. So this is the time to think about recycling as well. How can we recycle? How can we best use, these materials again and again?
It is one of the things that I absolutely love about electric motors. In my youth, I loved engines as well, and I worked on a lot of engines and stuff. But as an engine gets old, the components wear out, and it gets to a point where actually it's impossible to refurbish it. And relatively, compared to an electric motors are great because you can refurbish them quite easily normally. They don't need any mechanical attention really for many, many, many years. And you've got in kind of rail and marine, you've got motors out there that are still reliably delivering service that haven't been touched for 30 years or more. But then it's possible to kind of quite easily refurbish them. And, that's really exciting part of the EV future for me, that, when you look at a diesel engine or a petrol engine, as it gets older, the emissions go up. It gets harder to control. Start burning oil, lubricant oil, because of seals and things wearing out. But with an EV, it just keeps on working until one day it doesn't. But then you can refurbish it. There's no more emissions from it as it's degrading. Maybe it might get a bit noisier. That's the bearings kind of wearing out. But as in terms of like that recycling element of the economy, it does seem it's quite an exciting part of it for me. And I love seeing old electric motors that have been kind of cleaned up and refurbished and brought back to life. It's great.
Yeah, so I think that industry will grow as well, refurbishing electric machines. I mean, there's been this industry has existed for decades, and I think it's only going to grow, where you can refurbish. So mainly you need to probably change the bearings, but the windings as well. You may need to change the windings, especially as the voltage rating of machines is going higher. So we've had 400 volt machines going to 800 volt machines, going to 1000 and beyond. So that's where, we have to start looking at, what parts actually need refurbishing with increasing voltage. But yeah, it's an industry which can flourish, and recycling will become hopefully a big part of it in the future.
Yeah. So just, we're about out of time, but just if we could just kind of wrap up with your thoughts on the future and, in terms of your business and your activities, what are you most excited about that's coming down the line for you over the next year or two?
So the trend, this world is going electric. We know that. We are seeing that on a daily basis in the news. So electric machines are here to stay big time. There are many different kinds. So which type will lead, that has yet to be seen. But there will be, in my view, several different electric machine types. So there'll be permanent magnet machines always. There'll be switch reluctance, even induction machines. But because of material science, the efficiency will improve. More and more, sectors will start using electric motors, which are not just fixed speed, but variable speed, because variable speed gives a lot of advantages, especially in the pumps and fan sector, where cube law comes into effect. So if you drive a pump or a fan 20% less in speed, you save 50% of the electric. So the consumption drops by half. So especially in the sector such as pumps and fans, a lot of energy can be saved. Nearly half of the electricity used in the world is spent on running these electric motors. So if you reduce the speed a little bit, you'll save a lot of electricity. So that's where I see in HVAC, in industrial variable speed drive. So everything will become variable speed drive. That's where I see the trend going, other than complete industries changing, like the automotive market. It'll become completely electric. The aviation, the aerospace, it will be, it is changing to full electric. And I believe that is possible. And other marine is changing electric, railway is changing electric. So that's where I see it's heading. As far as the company is concerned, as I said, ePropelled is about technology. It's about reducing energy consumption. It's about improving the efficiency and lowering the costs in all these sectors. And as I said, we've got brilliant engineers. We want to train new upcoming bright engineers in this field, because this is the growing sector. And my favorite at this moment is bringing EDTS technology in the automotive sector, and to push the boundaries in the aerospace sector, where we plan to have propulsion motors running as fast as 100,000 RPM.
Wow. 100,000 RPM?
100,000 RPM. 100,000 RPM is not, it's not unique.
Dyson vacuum cleaner territory.
Yes, vacuum cleaners, people are attempting 150,000 RPM. If you go to the dentist, his tool is operating up to 200,000 RPM.
Proper turbo machinery territory.
Turbo, yeah. And even the turbines, the electro turbines generator we are using in cars, they're going over 150,000 RPM. In a second, they're up to that speed. So 100,000 is a target we want to keep for the aerospace sector, and I believe we can, reduce the size of big machines like, a megawatt and a half machine down dramatically. And of course, with machines, the cooling is an important aspect, and we are breaking grounds in the cooling of the electric machine as well, because machines do generate heat. How to cool it, how to recover the energy, and all that helps reduce carbon emissions.
Thank you so much for taking the time out to talk to me today. It's been a real pleasure. I hope all the listeners have enjoyed that. I've certainly learned a lot about what you guys are up to, and it's technology I hope to see in the market making a real difference. So thank you.
Great. Thank you, Ryan, for this opportunity, and hope to speak to you soon.